Okay, so there you go. Let me go. I need my tabs. Okay, so there is, if you guys go to the modules, there's the orientation module, and if you just go to the top, is all the LaTeX stuff. Okay, so I want to show you guys what each of these things are for. So the first one is it's kind of like a PowerPoint slide. Oh, I guess they changed it. It's broken down into parts. I definitely want to just, the first basic one will kind of give you an idea of like what is LaTeX, how is it used, what are like the features of it. And so here's a little presentation on just introducing someone to LaTeX that has never seen it. So that's what the first part is for, okay? Just to give you an introduction and like the formatting and all that stuff. The second one goes a little bit more, it's a little bit more specific. Let me see, did I open it up? Yeah. The second one's a little bit more specific. It's also introductory. And so then it does start telling you about like, what is, this piece of code supposed to do? And then it shows you like, when you enter this code, this is what's going to be shown to you in your document. And so it's also very introductory. Okay. Whoa. You guys just come from a class?
No, we all thought you were in another class. We were standing outside.
There's another class in there. There's another class in there.
Oh,
I was like, that's our.
I got nervous. I was like, what the hell is everybody? Okay. Yeah.
Like, they're definitely listening to say something. This is
Okay.
for the class.
12:45. Yep. I'll be here, guys. Don't worry. I know. So I was just telling everybody, I'm kind of giving you a quick intro on the LaTeX report. You guys have your first assignment on Monday. It's very low stakes, not that techy. It's just a little autobiography of your journey through math and how has it been since maybe elementary school? Like, has it been what kind of experiences have you had? Things like that. But I do want you guys to use the website called Overleaf. And the only requirement that's going to be part of the coding is to just make a table. That's all you'll have to do, okay? So I was telling everybody that on the top of your modules, if you go to module and you scroll to the top, are these links to kind of help guide you and help introduce you to LaTeX. The first one here, I just showed the class, has a PowerPoint that introduces to someone that has never seen LaTeX on what it is. The second one is when you guys came in, that's what I was showing you guys. It goes a little bit more into it. It gets a little bit more specific. And it talks about kind of Overleaf and what it'll look like and how you're going to use it. And it pinpoints a lot of like the buttons and what they do. The third one is a template that pretty much you just copy paste. Okay. So you'll click this template and then it's going to open a template of the type of things you guys are going to do in class. Okay. So it'll open this up. But when you guys open it, it won't let you edit anything. It'll just be view only, kind of like Google Drive. It'll only let you view it. As you're viewing it, after you've read the Learn LaTeX in 30 minutes, you'll have kind of an idea of what this page looks like here. So in this left region is where you enter your text, your code, and then on the right, it's what gets outputted. In this little box here is if you want to include a picture or like a PDF or anything like that, like some animations or graphics, you literally just drag them here and then drop them. And then later on, I'll show you guys, there's code where you can call that image so that it shows up in your document. Okay. But for now, if you'll open up this template. Is it a little small for you guys? Let me see. Let me just turn up the light. Yeah, this is a little small. Let's see, can I make it bigger? Oh, okay. So anything that is green are just notes. It's ignoring, it's not part of the code, it's just notes. So that's for you guys to read it. So I'm just telling you what this is. And you just, as you're reading it here, I'm just explaining like, okay, what is this for here? What is this for here? And so everything above that says begin document are like, it's called a preamble. It's just everything that's setting up the type of document that we're writing, because there's all kinds of documents, but we're just doing a nice basic article document. Okay. So all this, you can literally just copy paste it. After it says begin document, that's where you'll change some stuff. So here, maybe you're gonna do a report on problem number 20 in section 12.7 or something. So then that's where you'll change that. You'll put your name here. This you don't have to change, it's the class. But basically, this everything between begin document and at the very end that says end document, that's where you enter a lot of your writing. Okay. And like I said, I leave notes everywhere for you. So just when you get a chance, this is going to be a little bit of like independent study with me supporting you during office hours, or if you have questions after class, I can help you out. So take a look at that. Underneath that, let me show you an example. So for example, maybe you want to know what's the LaTeX coding for a very large, it looks like an inequality symbol. You guys see this bracket right here, but it's like a big, large one, right? So what is the code for that? How do I write that? So for example, in this case, it's this guy here, big Langle for left angle, and then big Wrangle for right angle, for the right side. Okay. So maybe you're wondering like, okay, I wrote this on my piece of paper. How do I put this in LaTeX? So underneath here is another link. We'll go there. That link, it's a little overwhelming, but it has a bunch of LaTeX code for a lot of math symbols. So like here, all these different letters. This is how you would write it in LaTeX. And so it's basically, if you want to look for something that, how do I code a particular symbol, you can go here. Or one of my favorite ones is called the Textify. So you click that link, it takes you to this page, and then you literally draw the symbol. So let's say I want to know, how do I make like an equal sign that has the equivalence squiggly on it? I'll draw it, and then it'll look for different types of symbols that look like that, and then it'll give you the LaTeX code for the particular one that you want. Okay. Later on, we're going to look at an upside down triangle called the gradient. So then I draw the upside down triangle. It'll look for it. But if you're in a coding class, a lot of the answers are on Google. Okay. And usually when you say, how do you blah, blah, blah in LaTeX, like the first two searches will answer the question. Okay. So I just wanted to kind of give you guys an idea of what that would look like when you guys go on Overleaf. Okay. So you'll go to overleaf.com. Oh, damn it. I'm already logged in, but let me log out. You'll go here, you just make an account, it's free. And once you make an account, let me go back. Oh, I already logged out. Let's see. Is it the right one? Hold on, nope. Give me a second. Okay, once you log out, you won't see all this crap here. You'll just see like a blank one here, but you go to new project, go to blank, or if you want to browse, okay? If you want to browse other kinds here, but you can go to blank, just say like homework or whatever you want to call it. And it'll be blank, okay? And it'll give you like the most basic structure here. So what you could do is you can go to the homework template, select all, copy, select all, and paste it, and then just recompile it. So now it's your document and you can edit it. Otherwise, it's not going to let you edit my template. Is that cool? Does that make sense? Okay. Then to submit it on Canvas, once your document, like whatever it is I'm asking you to turn in, you feel is complete, you're going to go to share. You're going to go turn on link sharing. And then you see right here where it says view. You will then copy paste this link onto Canvas. And that's how you submit your assignment. then I'll click it and I'll open it, and then I'm going to give you feedback on only the LaTeX stuff. Okay. But for Monday, all you have to do is basically from here to here, for example, from end document to begin document, where to go? Right here, okay? I'm not, and for this one, you're not doing a homework problem and a solution. So I would pretty much erase all of this. Let's see, all of that until the problem starts. Where's the problem? Problem right here for this assignment. And then I'll just say, I hated math when I grew up, whatever, blah, 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 blah. Okay? But then the only task for the Monday's assignment is to figure out how to put a table. That will be the only like codey thing that you're gonna kind of get practice on. Sound good? Yeah? Okay. All right, guys. So I just wanted to show you that. It'll be recorded. You can refer back to it later on if you need to. Oh, and then I wanted to show you my thesis in case you're curious. So I used LaTeX in grad school when I had to write up my thesis. And I just want to show you why when you go to university, they would like you to use LaTeX is because of the organization and how presentable all the math will end up looking. And you can use all kinds of symbols. And especially when your work is very messy, like it is in this whatever the hell this is. Referencing is really nice. When you submit it as a PDF, you just click it and it takes you straight to the reference. And so it's very organized, it's very presentable, and it's what the science community and math community use when they're presenting papers. Okay. So I just wanted to show you that. Yes. Nope. You're just doing basic stuff. Yeah. Nope, it's free. It's free and it's collaborative. It's like Google Drive. So you just have to put your email. Yeah, you could put your DVC email if you'd like. They don't spam you. They don't send you all kinds of stuff. And like I said, if you want to collaborate with a classmate, oh crap. If you want to collaborate with a classmate, you just share with them your link to edit, and then you guys can kind of work off each other and help each other out. Okay. All right, guys. Questions? Yes. Oh, yes. Sorry.
What was your thesis about?
Oh, my thesis. It was about something called a permutahedra, which is like oh, we're doing 3D. I can actually say some of this stuff. So you see how this has 3-dimensional points, and it has the numbers 1, 2, 3. Well, if you permute the numbers 1, 2, 3 to all possible permutations, and you connect them in a certain way, it turns out to make a hexagon. And you could do this for any n dimension. So if you have like 20 dimensions and you have all those points with all those permutations, and then connect them a certain way, it makes a shape called a permutahedra. And then what I had to do was, it had to do with some probability. Imagine I put this shape in a bucket and like I blew it up. And then when it blew up, its dimensional pieces came off. So like the edges came off, the corners came off, all its dimensional pieces came off. A certain number of them exploded into the bucket. And then you put your hand in the bucket and then you grab something. What's the probability that you grabbed an edge, for example? And then once you get the edge, you put it in a bucket, you blow it up again, and all its dimensional pieces come off. So you keep doing that. You can grab the edge back again. The edge can reappear again when you blow it up. So what's the probability? How long on average does it take to eventually just reach one of the corners? Yeah. So that model is the same model as if I had, let's say, a 20-dimensional permutahedron. And then I had 20 of you guys stand in the back of the room. You were all one group. I had you flip a coin. If you get heads, everybody that gets heads goes to the left. Everybody that gets tails goes to the right. Now there's 2 groups. then each group flips, and you keep doing that process until eventually nobody's in a group anymore. Everybody's by themselves. That process is the exact same process of the little bucket thing that I did. So it combined like probability. There's a way you multiply these shapes and like factor them. That's like the bucket. And something called combinatorics, which is the study of counting things. Yeah, it was cool. It's a cool project. And then I guess it has to do with optimization. That's more for the applied math. I just did the pure theory math. It was a fun project. I did. All right, let's see. So, turn off my sharing. We're going to take out with vectors today. You have taken linear algebra. Maybe you're a little familiar with them. If not, it's all good. I'm assuming you don't know what these things are. Normally, on some classes, remember how we had a warm-up on Tuesday? I usually will collect those warm-ups as part of like 2 points of the class. Or sometimes at the end of class, I have reflections. And then I collect those as well for points of the class. So, but today I don't have a warm-up because I wanted to go over the LaTeX course. So we're gonna come straight to it. We're doing section 2.2. On Monday we did three-dimensional coordinate system. Just to kind of get an idea of how to visualize this stuff. What did we say? What happens when you graph the equation? What happens when you graph an equation in R3 in 3 dimensions? What did we notice always happen? What did the graph always turn out to be? What kind of thing was it? Surface, which is what dimension? It's 2D, right? So we realize that whenever we graph an equation in 3-dimensional space, it always produced a 2-dimensional graph, which turned out to be a surface. So what happens if, let's say I want to graph a line though? I don't want to graph a surface. If I want to graph a line, we can't use an equation like you guys used, the slope-intercept equation for algebra, right? Because equations produce surfaces, not lines. So what's going to happen is to graph a line, we're going to need a slope. So give me a direction, right? But here, there's 3 dimensions, so slope will be a little weird. So instead of having the slope control the direction of a line, we're going to need a vector to control the direction of the line. And so therefore, we need to understand how to play with vectors. Okay? So, what are we doing now? We're doing that. Yeah. So we will eventually want to graph lines. So to do that, we'll need vectors. We need vectors. And you've never seen or heard of a vector. There's all kinds of definitions for it. So your textbook uses a very, very general definition. Okay. And then I'll try to add some visual stuff here. So we're going to say a vector is a quantity that has both direction and magnitude. Or sometimes we'll say it's an object that has both direction and magnitude. If you've taken linear algebra, sometimes a function is called a vector, depending on how they're defined. Okay? But in this class, we're going to do it very visual interpretation of it. And it usually has to do with like connecting points. Well, let's say we're in, we have point A here, and we have point B over here. I'm gonna draw a vector, so I'm gonna visually put a line, and I'm gonna put an arrow to give me the direction. Okay, this is telling me that an object, for example, will move from point A to point B. And the length of this will represent the magnitude of that. Okay, we're gonna call where it starts, that's called the initial point. And where it ends is called the terminal. And then there's going to be different ways to say the same vector. Okay. So for example, the vector connecting A and B, we're going to write it specifically as a different letter, but now I'm going to put a little arrowhead so that I'm telling the reader vector. Okay. And writing B as this vector, if I want to be more specific to my reader and I want to say it's not just a vector, it's a vector connecting point A to point B, you would also write it like this, equals AB, but now you put a line with that so that you're telling the reader it's a vector. So for example, if I want to write this in LaTeX, you would do slash, you would put vec, and then in squiggly brackets, you would put the letter V, and then it's going to output a V with an arrow on top. Make it. You eventually get that. Good. I'll throw some of those during class. So the direction is from A to B, and then in this case, the magnitude is its length. Which we're going to discuss in a little bit. Okay. But in this case, it's its length. We can also say, well, I'm looking at the same point A and the same point B, but this time I have the same magnitude, but this time it's going to point in the opposite direction. That. So is this vector the same as this vector? What do you guys think? Question?
No,
Yeah, you can do that.
I think it's the same direction.
You think it's the same or you don't?
It's not. The direction is different.
Gotcha, because the direction is different. Somebody else was gonna say. Same? Yeah, so because the definition uses both of these conditions, the vectors have to agree on both of those that they're going to be equal. But because they're not the same, I can't use V, so let's use W. I'm going to say W now is a different vector, but now what's the initial point? And the terminal? A. So now I'm going to write it in this direction like that to tell my reader it's going the other way. Some more definitions here. So let's define the question I just asked you guys. So we say two vectors are equal if they have the same magnitude and direction. Magnitude and direction. So this is about equality. And so yes, these two are not the same because they don't have the same direction. Then we're going to define the zero vector. That was funky. So the zero vector. Here, let me see if you guys can pick up the definition. What do you guys think the definition of the zero vector is if you think of these two conditions? Has no direction or has no magnitude? Close.
I guess the wishing side, if we have like You can define like.
I guess if I was to draw it, what would it look like? It would just be a point, right? So then what would be the magnitude of just the point? It would have to have magnitude 0. Yeah. So it's, we're gonna write it like this. We're gonna write 0. Oh, and then let me prepare you guys. There's hella notation in this class, and what you write will mean something completely different now. Okay, so if I just put the number 0 without a little arrowhead, that's a number. This is a vector. Okay, so the 0 vector is the vector with magnitude 0. And you can kind of argue that it has no direction or it has all directions. It's just there's no specific direction since it's just a point. Question.
Yeah, is there, like in geometry, you have like similar shapes, right? So is there terms of vectors that are like the same direction but different lengths?
The same direction, different.
Like there
There is.
basically.
There is. Yeah. We'll get to it later. They're like multiples of each other.
Oh, okay.
Yeah. We'll define that in a little bit. So magnitude 0, and we're going to say, and no specific direction. All right, and then last one here. What do you guys, I guess, what do you guys feel is the relationship between V and W, the way they're written? Like reverse, right? Like opposites of each other. So that's kind of what this is going to talk about. So given a vector V, it's negative. We're going to say it's called it's negative. It's negative V has the same magnitude, spelled that wrong, but opposite direction. If we grab these two, we can say that W is the negative of V. Like that. And we want to get that equation. So let's say we're in R3 and I have my point A and point B. There'll be a vector connecting those two, right? And if I move my hand, now I have a different vector connecting this different point and this different point, but it has the same direction and the same magnitude. So no matter where I move my hand, I'm getting all these different vectors that by definition have the same magnitude and have the same direction. It's just where they're located that's different, but they're all by definition going to be equal. Question.
Yeah, is there a notation for the directions and magnitudes of the vector?
There is notation for the magnitude, which we're going to get to in a little bit, and then there are ways to define the direction according to angles of how it's like slanted and all that stuff. Yeah. So if we have all these infinite vectors that are all equal to themselves, it might be a little hard to pinpoint to someone one specific vector that I'm trying to talk about. Okay. One way to do that is if I have the 2 coordinates of the points, then I can be specific about the vector. Okay. So what we're going to do is from all those vectors that are equal, we're going to focus on one special one that starts at the origin. And then all other vectors equal to that one are going to be like copies of it. And they're all equal to that. But that one itself also has a name. So notice there are infinitely many equal vectors, but only one with its initial point at the origin. At the origins. And so that's a special one, which we're going to define. And I'm going to show you guys some graphics as well. Actually, let me just show you. I'll bring this back if you're ready. Say. Okay. Let's go. There we go. Okay. So let's see. Let me go to. Whoa! Let's go. Move all the way down. Let me just step on the stupid one. There we go. Okay, let's see. So week 1, and then I have one with vectors. Here we go. Okay, so it's a little, the print's a little small. I apologize for that. But here's point A and point B right there, floating in space. And then here, to write out on GeoGebra the vector, you just put vector, and then you put the letter of the 2 points, so A and B. And then notice that that's the vector connecting A towards B like that. And then down here is the position vector. It's the same magnitude, same direction, but it starts at the origin. Okay, that's the special one we're going to talk about right now. And then notice I can move the position vector, or that this vector here, I can move it. Let me see if I have it right there. Yeah. And it can vary and could go all over the place. So all those different vectors, when I was moving my hands, that's kind of what this is doing. Those are all vectors located in different positions of R3, but they're all equal in magnitude and they're all equal in direction. Sorry. So what we're going to do is we're going to focus only on the one right now and on the one that starts from the origin and give that a special name. Okay? So let's see, let's define that one. A lot of definitions, I apologize. That one's called the position vector. So the position vector V, and now we're going to actually give it kind of like coordinates, but instead of writing it as a point, we're going to use the vector bracket. This is called the vector bracket. We're going to call its first as X component V1, V2, and V3, kind of like a point. Okay, so this position vector is the vector whose initial point is the origin, and terminal point, where it ends, is the point that has these coordinates, V1, V2, V3. So notice the notation that I'm using. If I put a parenthesis, I'm telling the reader point. If I put a vector bracket, I'm telling the reader vector. You guys are going to see these position vectors also. Let's draw a little picture here. Practice our R3 drawings from Tuesday. So it starts at the origin right here. And let's say this point right here is the point with coordinates V1, V2, V3. that position vector is the one that connects it to that point right there. But it starts at the origin. Okay. Let's say this point had coordinates 2, 1, 2, or let's say 3. Okay. You're at the origin. How far in the x direction do you have to move? In this case, 2 units or V1 units, right? So you would move according to whatever the x coordinate is. You would move this many V1 units, and then whatever the second coordinate is, that tells you how far you go in the y direction. This is not to scale, so maybe let's put a 5 here. But whatever it is, you move this many units, which is given to you by the y coordinate. So that's V2. And then what? What does this guy tell you? How much to move up? Perfect. It tells you that then you move up V3 units. So going back to your question, which is like, how do you annotate the direction of the vector? The position vector tells you to go from the initial point to the terminal point, you will have to travel V1 units in the x direction, V2 units in the y direction, and V3 units up to land at its terminal point. So it gives you kind of like the amount of change for x, the amount of change for y, and the amount of change for z. Okay? So actually, let me actually write that. This is like telling you how much you change in x, how much you change in y, and how much is you change in z to go from the initial point to the terminal. Let me give you another example in R2. Because everything that we're discussing also works in 2 dimensions. So let's say it's 1, 2, 3, 1, 2, 3. And let's say the vector starts here, and then it goes up here. And then that's the position vector. This is V. Okay. If that's V, how do you guys write this using this notation, according to this definition? These are called its components. These are called the components of V. Components of V. So in this case, for this specific example that I gave you, what are the components of this vector? How much does it change in the x direction? 1. And how much does it change in the y direction? 3 units, right? So then it would be that position. Okay. If you have to take physics, you'll see this notation as well. Let me show you what that would look like in physics. So in physics, you consider a force vector and a displacement vector. So the force vector, let's say it's an R3, okay? If you're doing something in R3 and you're moving an object from where it's initially located to where it ends up at here, there's a certain direction that you're going to push it. So there's a certain direction that the force is being applied in the x direction, a certain force in the y direction, and in the z direction. So that is specified by, I can write it as, how did I do here in my notes? Yeah, I wrote it like this in my notes. I said Fx, Fy, and Fz. This is the force that's acting on the object, but in the x direction, the force in the y direction, and the force being applied in the z direction. Where the displacement vector is talking about when the object moved from here to here, how much did it move in the X direction? How much did it move in the Y direction? And how much did it move in the Z direction? So then, they'll label it like this. And then we're gonna do some stuff with that later on, but for now, I just want to show you that this notation is talking about this notation. Okay? We'll play with some stuff like that later on. A lot of definitions right now, I apologize. It's just, some of you guys have never ever seen a vector. Or you've heard of it, you've never like really played with it much. So I know how to label a position vector the way we did it here, but how would I label the same vector, for example, if it was located somewhere else? Like if I just know the coordinates of the 2 points that it's connecting, how would I find its corresponding position vector? Okay, so that's the question I want to play with. Oh, sharing my screen. Hold on. Stop sharing my screen. So how do we find a vector connecting 2 points? Okay. So if I have 2 other random points located in R3, how the heck do I find its position vector? And what we're going to do is we're going to use this fact that we just discussed. V1 tells me how much change happens in X. V2 tells me how much in Y. And V3 tells me how much in Z. So that's what we're going to do. We're going to find the components of its position vector to give me that piece of information. So in your notes, draw a nice little R3 here, nice and big, so that you can label it in your notes. And let's say point A is here and has coordinates x1, y1, and z1. And point B is somewhere over here that has coordinates x2, y2, and z. And I want to figure out how I can tell someone that vector right there, since it's not located in the origin. So we know it has an equal position vector that has the same magnitude and the same direction.
So, the person probably not really knows that there's a different type of vector.
Then yeah, like if you're given 2 points, like if I give you two random points with actual coordinates, how do you find the vector that's connected? Yeah.
You break it down into x1 and 2 components, subtract x2 minus x1.
Correct.
So on.
Exactly.
You do some position by pursuing the organs.
Exactly. Yeah. Exactly. Since these tells you how much change happened in the x direction to go from initial to terminal. Exactly. We can use the coordinates of these 2 points to tell me how much change in x, how much change in y, and how much change in z. So this is my position vector here. But this one ends up at v1, v2, v3. We have that since these 2 vectors, by definition, have the same magnitude and direction, they're equal. And since they're equal, right, we know that v1 here is telling me how much change happens in x to go from initial to terminal. V2 tells me how much change must happen in y and how much change happens in z. Just like your guys' classmate said, well, I can find out how much change happens in x by subtracting the x coordinates, x2 and x1. I can figure out v2 by subtracting the y coordinates, And then I can figure out V3 by subtracting the V4. Yeah, exactly. Maybe that's that. And so this tells you now, which you're going to use till the end of week 16. You're going to use this equation, okay, or this like this formula. So the vector AB connecting points A and B is equal to the position vector given by the components that we just discussed here. So I will subtract x2 and x1, I'll subtract y2 and y1, and I'll subtract z2 and z1. You might forget this down the line. So some what's it called when you guys, like when you chant, when you say something in your head to help you remember that? What's it called? Mnemonic? Mantra, like, okay, mantra sounds more powerful. But it's basically, if you want to remember how to find the vector here, you always do terminal minus initial. Terminal minus initial. That'll help you remember. Terminal minus initial. To help you find the components of that circuit. All right, I've been talking too much, so let me have you guys do a little bit of, play with this a little bit. Let me give you guys some practice problems here, so help you connect all this. So for points A that has coordinates -1, 0, 5, and B, which has coordinates 2, 10, and 1, first find its position vector, V. Then for the point P, I'm going to give you a different point here, which has coordinates -2, 1, and 5. Find the point Q, the coordinates of the point Q, so that PQ equals AB. So let me have you play with those two questions. And similar groups that I put you guys on Tuesday. You guys, let's say, I think there's a unit here, right? And I had the inspiration here. We can do the YouTube here today. And the YouTube here. Okay. You guys can settle something happens about that. Yeah. So then you guys can come up here. Yeah. And then I have you guys do good. You guys here from work, you two. I think you four here were collecting, you were putting your thoughts together. I'll have you four here. And then would you need me? Oh, actually, you can join us. It's you three here, right? Yeah. Actually, no. And then I'll have you over there. Go ahead, try it out. Yeah, it's position vector AB. AB. For numbers, Sure, I'll write that so that.
Oh my God. No, I recommend that. Number two. No, he says, you want to triple minus three for x. So vector is equal to correct. And then the answer for number two, you're trying to put a coordinate. So you want.
Let me know if you have questions as I walk around.
I don't know what
For now, it's fine.
Yeah. What's the difference? Number one, I got a vector. Point two, I got 1 0.
A little bit quieter. All right, what'd you guys get for AB? 310 negative 4, right? You would do terminal minus initial, so 2 minus 1, minus negative 1 is 2 plus 1, so 3. 2 minus negative 1, and then you did 10 minus 0, just 10. And then 1 minus 5 gave you negative 4. What do these components tell you about how the vector's oriented? What does this part tell you? When you go from A to B. What does this tell you? Move 3, yeah. So the x, when you go from point A to point B, notice the x direction increases by 3 units. So this tells you increase by 3 units in the x direction. This tells you that increases in the y by 10 units. So you have an increase of 10 units. But this is negative. So it actually decreases 4 units in the z direction. Like that. Okay? And so if you're trying to find the coordinates for Q, and you know it starts at P, what a lot of people were telling me was, well, if these are the coordinates of P, then according to this vector, the X should increase by how many units? By 3 units. The Y should increase by 10 units, and the Z should decrease by 4 units, so that it has the same magnitude and the same orientation direction. So let me do this again. Let me be a little bit more algebraic with that. So here's another way that you guys can think of like this here, okay? You don't know the coordinates of this vector, right? We don't know the coordinates of that. So if I use my position vector formula here, and I try to find PQ, I know that I can, it's whatever this X coordinate is minus this X coordinate. So it becomes X plus 2. This unknown Y minus this 1. And this unknown Z minus 5. This is just me using my formula here to give me the vector, right? But this vector is supposed to be equal to this vector from what the condition says. So you know that this has to be equal to this vector here, because this is AB. And since I want both of these two vectors to be equal to one another, I want their components to be equal to one another. So then I want X plus 2 to be equal to 3. I want Y minus 1 to be equal to 10. And I want Z minus 5 to be equal to 4. So there's a different way of kind of doing what some of you guys were telling me, right? Solve for the unknown variable, minus 2. So that gives you that X is 1. Add 1, it gives you Y is 11. And then add 5, that gives you that Z is 1. And so then therefore, Q has coordinates 1, 11, and 1. Is that, I think, what most of you guys were getting with? Okay. That's more of an algebraic way of doing it. Where some of you guys were doing more, I guess, more of like a conceptual way of doing it. Which you guys were understanding that to go from P to Q, according to the directions of this vector, X needs to increase by 3. So if I add 3 to this, that gives me 1. Y has to increase by 10, which becomes 11. And then 5 has to decrease by 4, which becomes 1. That was another way some of you guys, which both correct. Okay? I think I cut it off here, right? Yeah. Let's see, where are we right now? Let's just do magnitude real quick, and then we'll take a break. Cool? Questions on either this one or this one? No? Okay. All right, sweet. Keep going. So now let's talk about magnitude. So this helps us it gives us the direction of the vector, right? It tells us how it's moving. So now we want to figure out, how can I tell how long it is? It's magnitude. So how do I find the magnitude of a vector? Visually, how are we finding the magnitude? How do you think we'll do it visually? What should we do? Find the distance, right? And in last class, we talked about how to find the distance between 2 points. So that's exactly right. So to find the magnitude, we just find the distance between 2 points, between the initial and terminal points. And terminal points. Let's give a definition for that. So we're going to say for a vector V that has components V1, V2, and V3, its magnitude now is going to have a notation. We're going to use kind of like, you know how when we wrote absolute value, it looked like that? And absolute value was kind of telling you like how far a number was from zero. But here for vector, we use kind of like a double absolute value symbol. And now it means magnitude versus absolute value. And so, since we know how to find the position vector, okay, which in this case is just V1, V2, V3, I want to find the distance between these 2 points, or if I have actual points like this one, I find the distance between these 2 points. And if you guys remember the distance formula, it is the square root of this squared plus this squared plus this squared, right? But these are really just V1, V2, V3. So then what ends up happening is the magnitude of a position vector is the change in x, which is V1 squared, the change in y, which is V2 squared, and the change in z, which is V3 squared. So that's how we're going to find it. For example, here, square this, square this, square this, add them, and then I take the other square root. One more little definition. Throw definitions out. We're going to say a vector with magnitude 1, that's a special kind of vector. We're going to call it a unit vector. A unit vector is a vector with magnitude 1. Magnitude 1. And we're going to use unit vectors a lot in this class. So again, just to give you guys a little bit of practice, are the following unit vectors. Try this one and try this one. Just be real quick at the unit vector. 1/3, -1, 0. 2, -1, 2. So see if you guys can determine if the unit vectors or not. What do you need to do first? You need to check their magnitude. And if it's equal to 1, then you're good. By definition, it's a unit vector. Okay, while you do that, let me prepare this. Tab something. -1/3, -1, 0, 2. No. Okay. Let's see, what did you guys get for the magnitude of this one? You should have got 1/9 plus 1 plus 0, right? Which what? 10? 10/9? Is that 1? Not 1. So no, it's not. Let's see this one. Here you square root, you do 4 plus 1 plus 4, which gave you what? 9, which is square root minus 3, and that's definitely not 1. So also no. Okay. So what's gonna happen in this class is we're gonna play all about with vectors, and sometimes you don't care about the length of the vector. You don't care about the magnitude. What's important is the way that it's pointing. So then what's gonna happen is we're gonna remove its magnitude and make it a unit vector. Okay. And so what we're gonna do right now is this guy right here is not a unit vector because it has magnitude 3, but we can find a unit vector that points in the same direction as this guy. Okay, question, yes.
Is there a lot more mathematical term for doing that?
I think it's called normalizing the vector. And so this is not a unit vector. It's not a unit vector, but we can find it's a unit vector that has the same direction. Has the same direction. What do you guys think we should do to that vector? How would we do that? I heard divide. The divide is magnitude off. But here's where we're getting into this weird thing where I know how to divide a number with a number, but this is asking me like, do I divide a vector by a number? And that's where it gets a little funky. We don't know what it means to divide vectors.
So the divide,
So that the way we're going to divide the vector is we're going to actually divide each of its components by its magnitude. Okay? And so let me show you that example. So we have what we're going to do now is let's find the magnitude of this vector, but divided by each component, like you guys said, by its magnitude. Divide each component by its magnitude. Yeah. Let's see if that works. So that should be the square root of 2/3 squared, which is 4/9, plus 1/3 squared is 1/9, plus 2/3 is 4/9. And then they all have common denominator. 4 plus 1 plus 4 is 9. 9/9 is 1. So yes, it equals 1. Okay. Real quick, let me just show you. So here is that vector. This is the vector that we're playing with. Whoops. Right here. And notice that when I divided each of the components by 3, I got this unit vector here. And it's smaller because it has magnitude 1 versus 3, But what I want you guys to see that it's actually also pointing in the same direction. Okay, and that's going to be important later on to do that. So one last thing, let's just say, how do I do that in general? Or literally what you guys just told. And so in general, if V has components V1, V2, and V3, its corresponding unit vector is, and we're going to label it like this, V divided with its magnitude. But remember what it really means. It means that you're dividing each of its components by that magnitude. A lot of writing, sorry. That's what it really means. So when you see this, it really means that. And so we're starting to get to a territory where we're now doing operations on vectors. Here we're doing this funky like division thinking. Let's take a break. Perfect. Still o'clock. Let's take a 10-minute breather and let's resume at 2:10. We'll get some latte, some candy. Yes. Yeah, in this case it is you're dividing, yeah, the third of it's like, because you divided everything by three. Right? So instead of something being changed by a certain X, a certain Y, and a certain Z, everything's 30. Good. All right, pause it. Yeah, so if you wanna put that, this is called normalizing a vector. Normalizing a vector. Into a unit vector, that's right. Yeah, so if you hear that, like, oh, the vector was normalized, that means you found its corresponding unit vector. Okay. Yeah. All right, guys, so now what we're going to focus on are operations, things that we can do to vectors. So we can play with them a little bit better. Make sure I'm recording. Yep. All right, so operations on vectors. And I believe today we're only doing 3. Yes, we're only going to do 3. So the first one is called scalar multiplication. Scalar multiplication. And so this word scalar, what does that mean? So let's let C be a real number. In this class, a real number is called a scalar. Okay? Called a scalar. It just means a number, or a real number in this case. And V, a vector. V with components V1, V2, and V3, a vector. we're gonna say the scalar multiplication C times V means, what do you think it means? What are we doing with this number in the vector?
You just multiply the C into each of the components.
Exactly, yeah. So C gets multiplied with the X component, C gets multiplied with the Y component, and C gets multiplied with the Z component. So visually, what do you guys think this does to the vector V? Stretching, it's like shrinking it if C is very small, but if C is a big number, then it stretches. Okay. Good. So, let me do a little example, but then kind of, I'm gonna break down what's happening underneath that. And I'm gonna ask you guys, kind of like a proof question in a little bit. So, for the vector V, let's say it has components 1, 2, 3. Notice that if I do negative 2B, according to this definition, I multiply all those components by negative 2. And as you guys said, as a consequence, it just visually, it's going to stretch it. It gives me negative 2, negative 4, negative 6. This is a, when you do scalar multiplication, what is the result? Is it a number or a vector? It's a vector, right? I know it seems a little silly me asking you that. I'm going to ask you guys that later on next week. In this case, not only did it stretch it, it kind of like also reversed the direction because it negated it, right? It's going to make it point in the opposite direction. So here's what I want you guys to note. When we found this vector, if I want to find its magnitude, if I want to find the magnitude of this new vector, I want to see what is the relationship between the magnitude of the original vector and the magnitude of its now stretched vector. Like, what is the relationship between them? What do you guys think the relationship is? You guys said it stretches it, right? But specifically, how do you think it will stretch? By what factor? What's your guess? If V, let's say, had magnitude 5, what do you think the new magnitude of this vector? In your head, what did you guys do? Doubled it, right? Yeah, it's negated, so it's just pointing in the opposite direction. You guys you're saying that it might just also stretch it by a factor of 2, right? Let's prove it. Let's prove that that's true. So if I go off of this definition, this vector is this vector. So I'm really finding the magnitude of this vector. And so this is when you guys take higher level math, you have intuition about certain properties, but then you're like, okay, but now I have to prove it to the reader that it's true, not just my intuition. I want to show it's actually mathematically true. So then I'm going to do this. We're going to go off the definitions. The magnitude of this is the magnitude of this, and then by definition, this is the square root of this squared plus this squared plus this squared, which gives you, what's that? Help me out here. This is 56, right? 56. What is this break up into? Can we simplify this here? 2 root 14. 2 root, so is that 4 times 14? Is that what you guys did in your head? Yeah. Okay, so then it's the square root of 4 and the square root of 14. 2 root 14. Okay, the 2's coming out there. That's good. Now, what do you guys think root 14 is, though? If I want to go off of that question, that property that you guys told me, what would you want this to be? You would want this to be the magnitude of that. That way I can now mathematically say this double the magnitude of B. So let's see if that's true. So can I write 14 as this squared plus this squared plus this squared? This squared plus 4 plus 9, is that 14? Yes, it is. And because I can write it this way, now I can say that's really just the magnitude of B. Oh, yeah. And so in this case, what we said is true. The relationship between this new vector and B is that you do double its length. Questions? All right, I'm gonna have you guys do a little bit harder one. Okay? Just to kind of. Okay, let's see. Be a scalar. And B be the vector with components B1, B2, B3. So we just answered this question for this particular example, for this particular vector. So then you do this in the upper division class, you're like, okay, I proved this. But then now what do you think is the next question? A bit higher level question that I can ask regarding this. Is it true in general? Like, will that always be true? So, so you have this. So what I would like you guys to do is using algebra, prove, similar to this process, but a little bit more complicated, prove that the magnitude of the scalar multiple CV is really just the absolute value of C times the magnitude of the vector. Similar to kind of how we did it here. But now there's no numbers. Okay? See how you guys can try to cook that up. Work with your groups.
I was thinking that
Remember, try to use a definition. That's my hint. Try to use a definition. That will help. Okay?
Try and separate it out inside of the try and separate it out inside of this. Now you get CD1, all squares. That's something that I also.
When you guys are doing proofs, you gotta make sure you show your algebra. Square root of that is like C, right?
Yeah, it would be the, I guess, problem is it C squared or C times U squared? And that's kind of where it's. I mean, but if we were so like yeah.
Okay. Keep doing a little more algebra inside the square root.
It's all behind the square root.
Yeah. Make that a problem.
One little property was algebra and square roots, so the variable space becomes the absolute value.
I didn't do this all day.
I was like, that makes sense.
That's really.
That's true. So we could, yeah, oh yeah. I was just thinking that you could do like,
I don't get a spaceship. I'm all the way.
Is there something to do with the only?
Let me see, did you figure it out?
Yeah, yeah, no. Well, no, but this. Because, well, because we're supposed to, because we have some volume. I'm talking about it. Or is it like? Okay, just me and the friends. Okay, yeah. I could get rid of. Like, yeah, I remember. Yeah, we'll get that, because, oh, I just like. Okay.
All right, guys, let's see. Looking good, looking good. So it looks like most of you guys started here. So let me give you guys a little format of how a proof looks like, okay? It's not just like algebra, there's like kind of like a little structure to it. So normally when you're doing a proof, you tell the reader, okay, I'm going to start my proof here. And then you start showing your work. So in this case, we have this here. And I noticed most of you guys use the definition, good. Usually with proofs, that's kind of a strategy to start in, is with just things you know about definitions and see what it can give you. So you guys did that correctly. You wrote this as C V1, C V2, C V3. And then you said, okay, I'm finding the magnitude of that. So then you use which definition? That was this one. And then from here to here, what did you guys use? The magnitude definition, which is related to distance point. So magnitude definition says each component needs to be squared, right? So then that's right. Most of you guys caught that. You have to square the whole thing, not just the V1. CV2 squared plus CV3 and all that squared. So you use the magnitude definition, and then from there you just did some algebra. All of these get squared, right? So all the C's get squared. So this gets squared, this gets squared, and this gets squared. And then from there, what did you guys do? You factored out the C. I'm still gonna leave it inside though. I factored out the C like that. And then you square rooted the product, right? So you did the square root of this guy, and then now you split it up with the square root of this one. And then from algebra, what's the square root of a variable squared? Absolute value of it. And then this, by definition, it should be the magnitude of V. There we go. And then the way you tell the reader, I'm done with my proof, they put a little box. And tell the reader, I'm done. That's where my proof is. Okay? You'll see that in the textbook. It's like a random little box. All right, beautiful. Good job, guys. You do your first proof. Okay. So that's scalar multiplication, and this is a property that we just proved. So then the next one is what's called vector addition. You do that a lot when you take physics. Add vectors left and right. So vector addition. The definition isn't so complicated. So we have that for vectors V that has components V1, V2, and V3. And let's call the second vector W with components W1, W2, and W3. I want to add the vectors. I'm going to produce a different vector. But now this new vector tells you for the X direction, you increase by V1, but then you also increase by W1. So then you add those components together. And then the same thing for the Y components. And then V2 plus W2. The Z's increase by V3, and then by W3. It's more fun to do it visually than algebraic. So visually, if I have V like this, let me slow down. Let's say V has this magnitude, and it points kind of diagonally up. And let's say I'm going to add it with W. That goes straight up, like that. And let me, no, I'll leave it there. So then when I add these guys, I'm going to start with my initial point where V starts. It ends up at its terminal point. But then from there, now I go according to W. And I move it up now. So now from this point, it moves up to its terminal point. And so then the resulting sum vector starts at V, but ends at W. And this is what we're going to call V plus W. Like that. Okay. Let's put some numbers in here. For those of you that take physics here, let's go to R2 real quick. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And let's say V is that vector we were looking at earlier, 1, 3. This is V right here. So V is the vector 1, 3. And W is the vector 2, 0. Two, 0. Let's see, what does that look like? That's 2, but Y doesn't go up. So it just looks like this. But if we want to add the vectors this way, I start from the initial point of V and then move to this terminal point. And then from there, now I continue with W. So I think of moving this vector and moving it up here now. And just move 2 units that way. So then this says that if I do V plus W, I add 1 plus 2, which is 3, and then 3 plus 0, which is 3. It should result in the position vectors 3, 3. And notice that if I go 1, 2, 3, 1, 2, 3, it exactly lands at the sum. For the sum vector. Yes, question.
You guys keep W with V as well, or just be a parallel dimension?
Correct. So that was the property I was going to have you guys notice, that I could have also done W plus V. And then I just basically do this plus this, but I still end up with the same vector. And visually, that means that now I start with W, but then I go 1 over and then 1, 2, 3. So if I would have done it this way, you get this nice little parallelogram. But this right here is special. You guys remember what that's called when 2 things add and they give you the same result as if you swap them? Commutative. The associative one is when you like the order of how you add it, right? So yes. So notice that vector addition is commutative. Is commutative. You can swap them and I'll get the same thing. All right, the last one we're going to talk about is subtraction. Very similar, but drawing it could sometimes be a little bit more complicated. So again, let's say we start with vectors V and W. So for vectors V having components 1, V2, V3, and W, W1, W2, W3. This time we're going to do minus. We have them, we're going to subtract them. It's pretty straightforward. We just subtract a component. Nothing too crazy. We're going to see some crazy stuff next week. This one's pretty chill. So let's do the same. Let's try to draw in your notes the same vectors that we drew here for V and W. So if I have V as that, and I'm going to subtract W, the same ones that we had before. Just like you guys learned in algebra, when I subtract a number, I can think of it as adding it by its negative. So we're going to do the same thing. So if I subtract W, that's the same thing as if I have V, and then I add, it's negative. What is this negative going to do? Exactly, this goes in the opposite direction. Right. And I know how to add vectors now visually. So then what ends up happening is I get, I start with V, and then I add the negative, so then where I end up, I now bring it down. And so I started here at V, and then I ended here at minus W. So then this is the difference vector. This is okay. Okay. Turns out your textbook doesn't do this. Okay, which is a little bit more like it's a little more straightforward because of the way we added it. But I'll show you.
Which direction is it pointing to?
So for W, it's pointing up, and then we flipped it so that now minus W points down. And then therefore I'm doing V, which starts here, goes diagonally up, but then minus W starts here and then brings it back down. So then the minus vector starts at the initial point of V, but it ends here. Okay. This is how your textbook's going to do it. They instead do V, and then they put W, not minus W. They put their initial points together. Like that. And then this vector that ends at W and goes towards V is this vector here. Okay. Why the heck is that true? Well, because if I have V, and then I minus W, the way we did over here, these two green vectors are exactly the same magnitude and the same direction. So that's why they're trying to be the same equal. But they're going to use this version instead. They put the two initial points together, and then they have V. No, what they do, but they do V. I guess they start with V, and then it ends here. I'll refer back to this again. Okay, you can go this way, but let me actually tell you why they do it. The reason they do it this way is because down the line we're going to have curves. There's going to be curves. And then we're going to do like calculus on it. We're going to do derivatives and all that stuff on curves. So what's going to happen is you're going to have two vectors touching the curve like this, right? Imagine there's a curve like this. You're going to have two vectors that are kind of doing this to it. And this vector connecting this vector, the vector connecting these two will be the difference vector. And it's easier to do it the way they do it than the way we did it when it comes to that side. Okay. Well, we'll do that later. Don't worry. So with these three operations, scalar multiplication, addition, and subtraction, we have a good amount of tools now to do some cool stuff with it. If you're in linear algebra, this word might sound familiar. The last thing I want to discuss in this section is what's called the standard basis vectors. And it uses all these operations to help us do this. Give me a random vector, three-dimensional.
1 to 1.
Okay, consider the vector 1 to 1. 1 to 1. Give me a different number besides 1. 5. So when we have this vector, we can think of this vector as a sum of three different vectors, where it's going to be 1, but then 0 is 0. everything's 0 but 2 in the middle. And then everything's 0 but 5 with the third component. Notice that if I add those three vectors, you get 1 plus 0 plus 0, that's 1, 2, and then 5. It gives you that, right? And I could have done that to any vector, depending on the numbers you guys gave me. But then this vector, I can think of it as a vector I multiplied by 5. So I can factor out of 5. Kind of like undo the scalar multiplication. So I can take out a 5 from here. What can I take out from this one? The 2, and then this one, I guess a 1, right? So I can think of this vector as this 1 times this vector here, which is just 1 times that itself. And then here, I can think of it as 2 times the vector 0, 1, 0. And then here, I can think of this vector as 5 scalar multiple with this vector here. And I could have done that to any vector depending on the components. Yes.
Is this like the matrices thing?
That's different, but it's similar to the linear algebra. Yeah, similar. I think they call it like a linear combination or something. So that's basically what that is here. Okay. So because I could have done this to any number here, I just factor out all those numbers, and I always end up with this vector. I always end up with this one, and I always end up with this one. So these are special, and these have particular notation for them. We're going to call this vector that has 1, 0, 0, the I hat vector. Okay. This one here that has everything 0 but the y component be 1, the j hat vector. And then this one's called the k hat vector. So I could do that to any. So we call these vectors the standard basis vectors. They're all based off of these three vectors, and I can just do scalar multiplication with sums and differences to always produce any vector in R3. So A hat is 1, 0, 0, J hat 0, 1, 0, and K hat is 0, 0. And so that means that now this vector, I can kind of write it like a polynomial, meaning I can write this vector as 1 I hat plus 2 j hat plus 3 k hat. Oh, sorry, plus 5 k hat. What kind of looks like polynomial-ish. And that's going to be true for any vector. Any vector v that has components v1, v2, v3, I can write it as v1 I hat, v2 j hat, and v3 k hat. Has anyone seen these in other classes? Linear algebra? Okay. No physics or engineering?
No.
Did they use it? Okay. Sweet. You're seeing it. It's always cool once the more like courses you take in your academic career, the more like things start to converge. And it feels pretty cool. You're like, okay, things are connected. It doesn't matter what I do. Because in the beginning, it's like, why do I care about all this crap? Okay, I have some comments and then I'm gonna have a worksheet that I want you guys to practice on. So just a few comments. So the first one is this standard basis vector, this is an R3. But you can technically also do this in R2, 2 dimensions, 4 dimensions, right? So in R2, we have I hat is just 1, 0, and J hat is 0, 1. Also notice they're all, what's their magnitude? They all have magnitude, so they're all unit vectors too. Right, and we've been only working with R2 and R3, but my other comment is vectors can be defined in any dimension. Any dimension, 20 dimension vectors. The set of n-dimensional vectors is labeled with a capital V and then a little n. Okay. And then the vectors just have n components, so v1, v2, all the way to vn. Everything we've done today also works for these higher dimensions. Sums, unit vectors, all that good stuff. All applies to that. It's just weird to draw. Okay. So I have a short handout, just a few problems to kind of have you pick your brain at this. And the solutions will be posted on Canvas. Okay. So let's see. I got 106 over here. 1, 2, 3, 4, 5, 6. Also, I couldn't fit it, but there's also more properties that might be used in your homework that are written on the top of the handout. There's so many. I was like, let me just focus on the main ones. Grab one, pass it back, please. 1, 2, 5. Yeah, the first one is kind of considered like a proof. Huh? This is not part of your homework. This is just class exercise. Okay. Yeah. Yeah, the first one is kind of like a proof. Oh, but visually.
So
Like with lines, yeah. Yeah, yeah. You can make up your own 3 vectors. Sweet. All right, I'm seeing some things a little different in your guys' sheets. Can I just have you guys quickly compare real quick what you have? Just show your classmates your work. See if they agree with you, because some things are not matching up.
Yeah. I was literally just writing this whole thing, like, wait a minute. Should the parentheses are like, let's keep it together now. I think you could timely just say you're around it, but then, yeah, but it doesn't really matter, so, you know, or whatever time you're. Yeah. We draw you that same. The way it's set up.
No matter what we're doing.
Yes.
You guys do that, let me post the solutions. Solutions will be in the same page where you guys see the recordings and the notes, okay? That's where they're gonna be. Two. The solutions include a bonus if you want to try it out for the worksheet, okay? This is the bonus. If you want to try out that bonus. Let me post. Come in.
Oh, yeah.
So usually when I give you guys handouts, they're problems that can help you during class, so that if you're on the homework, you can reference it. I don't collect those ones. They're additional support.
I got this.
It looks, it's nasty, but I don't think it's wrong. Let me see. It's not wrong.
Oh, okay.
Yes, I'll look. Let's see. I know that sometimes they do like a European version or something. Maybe bring it to me. Yeah, because I feel that we have the same.
Oh, yeah. It's all about. It's like. Oh my God. That's last one.
You want to check your solutions? They're in the week 1 video and media page. I just posted them.
Like one day, I was getting that kind of screen, so I wanted to that's the.
That was good. No, no. Wait, it's, we end at 3:15, huh?
Yeah.
All right, we're gonna take a field trip, okay? We're gonna take a little field trip. Yeah. So let me just clean up. And then, my notes will have a little piece of 12.3, but we're just gonna do that on Monday or Tuesday, okay? So ignore that part. Close it out.